Okay, very good afternoon, one and all. Today we can introduce the module 3. Okay, today we can introduce the module 3, namely phase shift keying technique. Phase shift keying technique. Okay, so in the last class, last two classes, okay, we completed the module amplitude shift keying technique. And we have defined the basic expression for ASK. What is the basic expression for ASK? It is same as that of amplitude of carrier. The amplitude of ASK signal is same as that of our sinusoidal carrier for the data bit 1, and for the data bit 0 the magnitude is 0. Okay. Now and how can you define in terms of power dissipation, power dissipated per symbol? You can replace amplitude of carrier as root 2 ps. Okay, if you replace the amplitude of carrier as root 2 ps, you can represent the ASK signal as root 2 ps into cos omega ct. That is for the data bit 1, and for data bit 0 it is 0. Okay. And similarly we have gone through the generation and detection of ASK. See, the generation and the coherent detection principle is to make use of a multiplier section. Okay, in the transmitter section, multiplier simply takes the product of unipolar energized and carrier to generate BASK signal, amplitude shift keying signal. Okay, in the coherent detection, same multiplier is used with the synchronous carrier as other input. So what is the receiver input? It is binary ASK signal. So binary ASK signal along with synchronous carrier, both are fed to the multiplier. This is in the case of coherent detection. Both are applied to the multiplier, followed by the low pass filter and decision device. You will get the you can recover the digital signal. And similarly, what are the blocks in non-coherent detection? In non-coherent detection, we'll make use of envelope detector followed by low pass filter and decision device. Already I told you that the low pass filtering and decision device followed by low pass filtering followed by decision device are the common terminology used in like digital detectors. Okay, so these are the two common blocks used for any kind of digital demodulators. Okay. And what is the basic difference between coherent and non-coherent? In coherent, we'll use of synchronous carrier, so the probability of error is less. In non-coherent, we don't make use of synchronous carrier. Directly, it uses a rectifier consisting of like envelope detection. Okay, so in order to extract the envelope or amplitude, we need the envelope detector. So envelope detector followed by the low pass filter and then followed by decision device are the fundamental blocks of non-coherent detection of BASK signal. Okay, like this we calculated Euclidean distance and we got it as root over ES, that is root PS into TS. And similarly we calculated the bandwidth of ASK signal and we got it as 2FB. Okay, but everything we did, but what are the drawbacks of ASK and why we are reading the next module, the phase shift keying, why we have so many applications for PSK over ASK? In the case of amplitude shift keying, the main drawback is that it has like the Euclidean distance is very less. Because the Euclidean distance is very less, the spacing between the two levels will increase. Once the isolation between the 2 points increases, it is very difficult to detect and distinguish the bit levels at the receiver section. Okay, so that is the main drawback of ASK. And one more thing is it is highly susceptible to noise. Because ASK signal consists of amplitude variations. So its probability of error is high because Euclidean distance is less. Once the probability of error is high, what happens to our SNR? It will reduce. So probability of error is high in the case of ASK signal, and because it is highly susceptible to noise, we are opting the next type of keying technique called as phase shift keying. Okay, so here in the case, so while generation, the principle behind ASK and PSK is almost all same, but in the case of PSK, we can observe phase variations of the sinusoidal carrier. Okay, compared to ASK having amplitude variations. Okay, but the generation principle is same. In the case of ASK, unipolar energized and carrier are applied to the like multiplier. But here, instead of unipolar, if you make use of bipolar energized, okay, bipolar energized and carrier, if both are applied to the multiplier, you can generate PSK signal. Okay, so we can discuss all these points in the today's class. Let us move forward. Okay. Now, what are the outcomes of this section? So, each and every student should be able to interpret the performance of PSK transmitter and receiver sections. Okay. Now, let us move to the PSK, that is phase shift keying definition and its general equation. Okay. So, how can you define phase shift keying? The phase of the sinusoidal carrier, is switched between two levels 0 and 1 of the input signal. Okay, the phase of the sinusoidal carrier is switched between two levels by keeping the amplitude and frequency of the carrier as constant. So, in the case of PSK, we are maintaining the amplitude and frequency of the carrier as constant. But what is the variable parameter here? Phase. So, phase of carrier will vary. Now, how it will vary? So, the thing is that how we can vary. How we can vary? That phase variation depends on the number of bits transmitted per symbol. Number of bits transmitted per symbol. For example, if you consider binary PSK, in binary PSK, we know that only one bit is transmitted per symbol. Only one bit is transmitted per symbol. If one bit is transmitted per symbol, how many like amplitude changes we have in BASK? Two amplitude changes. That is one and second one high level, second one is low level. Similarly, in PSK, in binary PSK, if one bit is transmitted per symbol, we'll have two phase variations because 2 power 1. So, one bit is transmitted per symbol. So, how many changes you can provide? 2 power 1. That is, for a binary PSK, we will have two phase variations. Two phase variations. Now, here I am defining the binary PSK signal. Okay, with the carrier assumed as AC cos omega CT, and let input be the digital signal. Now, how can we define PSK signal? It is defined as same carrier phase. See, I am representing AC cos omega CT for data 1. When input x of t is equal to 1, what is the PSK signal? AC cos omega CT. Can you identify any phase difference between this value and original carrier? No, there is no phase change. Phi is equal to 0. So, whenever the input x of t is 1, we don't have any phase variation. Okay, and we will have phase variation whenever x of t is 0. How much phase variation? Phi is equal to 180, because here in BPSK we have only two phase changes. One is no change and other is 180 degrees change. Either 0 or 360. First phase change is 0 or 360. Mean that there is no change when data is equal to 1. When x of t is equal to 0, 360 divided by 2. So, you will have get phase change at 180 degrees. Okay. Please keep phi is equal to 180 when x is equal to 0. In binary phase shift keying, we'll transmit only 1 bit per symbol. Because we transmit 1 bit per symbol, here we'll have two phase variations. One is 0 and or 360, and second one is 180 degrees. Okay. So when x equal to 1, here we don't have any phase change, that is 0 degree phase difference. When x is equal to 0, sorry, when x of t is equal to 1, we don't have any phase change. That implies phi is equal to 0 degree or 360 degree. When x of t is equal to 0, we have some phase change. That phase is of 180 degrees. So please tell me AC cos omega ct plus 180 degrees. How much? Minus AC cos omega ct. Okay. So expression for BPSK is AC cos omega ct when data is equal to 1 and minus AC cos omega ct for x of t is equal to 0. Okay, we can discuss the 2 points in the next slide. Please observe. So what is meant by binary PSK? In binary PSK, only one bit is transmitted per symbol. Only one bit is transmitted per symbol. That's why we already learned that bit duration is equal to symbol duration. Okay. And the second point is binary PSK. The other names are 2-array PSK or phase reversal keying or biphase modulation system. But in the case of binary amplitude shift keying technique, BASK is also called as on-off keying because it acts as an on key when x of t is equal to 1 and 0, that is off key, for data is equal to 0. But here in the case of binary PSK, we will have phase reversals. Why phase reversal occur here? Because it has only 2 phase changes because we are transmitting only 1 bit per symbol. That's why it has only 2 phase reversal. What are the 2 phase changes that we can provide? Make 360 degree by 2. So one is 0 degree or 360 and second one is 180 degrees. So in binary phase shift keying, sine wave carrier undertakes 2 phase reversals because we will transmit 1 bit per symbol. So what are the 2 phase reversals? 0 degree and 180 degree. 0 degrees and 180 degrees. Okay. Please observe the next point. This BPSK is similar to double sideband suppressed carrier modulation. So I think you can remember the DSBSC modulation technique which you studied in AIM technique. In analog communication subject, you studied double sideband suppressed carrier modulation. Okay, in AIM. So almost all the output of BPSK is same as that of DSBSC signal. Okay, except that the input used in DSBSC is message signal is analog in nature and here the message signal is digital in nature. Okay, except that almost all the output resembles to that of binary ASK. Binary ASK. Okay. Now, here please observe this BPSK signal is similar to double sideband suppressed carrier. Okay. Now, what is the simplest form of PSK is BPSK, where n is equal to 1 bit per symbol. If n is equal to 1 bit per symbol, how many phase changes you will get? M is equal to 2 power 1, that is 2 power n. So, 2 phase changes you will get. One phase is 0 degree or 360 degrees for input 1 and the other is 180 degrees for input 0. Okay, so you can be more clear if you observe the waveforms shown here. So you can observe 2 waveforms. One is the first figure, second figure is BPSK output. So what is the input? Digital signal. So here we consider the binary sequence 10 10 10 10 10 10 10. For the digital signal, okay, you have generated BPSK signal. You have generated BPSK signal. You have generated BPSK signal. If you observe BPSK signal, please observe carefully. For the input 1, you have directly represented the sinusoidal waveform. Here down to that we represented sin omega ct minus sin omega ct like that. Here they assumed the carrier as sin omega ct, okay, as a sinusoidal signal. So whenever the carrier is a sinusoidal signal, for the input data bit 1, for the input data 1, the BPSK has same phase as that of carrier. For the data bit 0 or when x of t is equal to 0, BPSK has 180 degrees phase change, 180 degrees phase change to that of carrier. Similarly, please observe third bit. If you observe third bit, it is data bit 1. If the data bit is 1, we will have same phase as that of carrier. If the data bit is 0, we have 180 degrees phase shift. So similarly, whenever the fifth bit is 1, so we will have same phase as carrier. So 0 degree or 360 degree. And if you observe last bit, LSB bit, it is 0. So we have 180 degrees phase difference to that of sinusoidal carrier. So the corresponding angles are shown down to the BPSK waveform. So the corresponding carrier representation is sin omega ct when data bit is 1 and minus sin omega ct when data bit is 0. This is when carrier component is sinusoidal signal. Here we assumed the sinusoidal signal as cosine. Here we assumed the carrier in the form of cosine component. Okay, so that's why while mathematical analysis, so that you should be compatible with all the techniques. So in ASK, PSK, FSK, let us consider the carrier in terms of cos omega ct, so that you can compare the mathematical expressions for all the techniques. It will be like flexible to you. Okay, now let us move to the next slide. So in this slide, we can discuss the mathematical expression of BPSK. Okay, so what is the general expression for BPSK, PSK signal? AC cos omega ct plus 0 degree. Okay, because plus 0 we did not represent it. When input x of t is 1 and when x of t is equal to 0, phi is 180 degrees. Phi is 180 degrees. So general equation is AC cos omega ct plus phi, and phi is equal to 0 when x of t is 1 and phi is equal to 180 degrees when x of t is equal to 0. Okay, please substitute the value of phi as 180 in the x of t 0 expression, because in x of t 1, if you keep omega ct plus 0, it will be same AC cos omega ct. So you will have phase change only that occur at x of t 0, and you will get the same phase as that of carrier when x of t is equal to 1. Okay, now please substitute phi is equal to 180 when x of t is equal to 0. So cos of omega ct plus 180 degrees, how much? It is minus AC cos omega ct, because cos 180 plus theta is minus cos theta. Cos 180 degrees plus theta is minus cos theta. So that's why you will get minus AC cos omega ct when x of t is equal to 0. When x of t is equal to 1, there is no phase change between the BPSK signal and sinusoidal carrier. Now, let us rearrange the above expression in terms of bipolar energet signal B of t. What is B of t? You are assuming B of t as a bipolar energet. Okay. So in order to generate the BPSK signal, let us represent the expression in terms of B of t, bipolar energet signal. So B of t is its magnitude is plus 1 when the input x of t is 1. When the input x of t is 0, its magnitude is minus 1. Its magnitude is minus 1. Okay. So what we did here? Here we considered, please observe the second equation shown in the rectangular block. It is AC cos omega ct when x of t is 1, and it is equals to minus AC cos omega ct when x of t is equal to 0. Okay, so what we are going to represent now here, in both the values, AC cos omega ct is common, but the difference exists from the sign. So take plus or minus 1 as B of t, and let us rearrange the above expression in terms of B of t. So upon rearranging, you can represent BPSK signal as B of t into AC cos omega ct, B of t into AC cos omega ct. Okay, so that is equals to plus or minus AC cos omega ct when B of t is equal to, where B of t is equal to plus 1 when x of t is 1 and it is equals to minus 1 then x of t is equal to 0. Okay. Now, so this is about the mathematical expression for BPSK signal. So what is the conclusion here? You can represent BPSK signal as B of t into AC cos omega ct, where B of t is equal to plus 1 when input x of t is 1 and minus 1 when x of t is equal to 0. If you replace B of t, you will get S BPSK of t as AC cos omega ct for data 1 and minus AC cos omega ct for data 0. Okay, this is about the general expression for BPSK signal. Please recollect, please try to compare this BPSK signal with BASK signal. Try to compare this equation with ASK signal. In binary ASK, when x of t is 1, it is same, that is AC cos omega ct. When x of t is 0, ASK signal is magnitude is 0, but here it is minus AC cos omega ct. In terms of bipolar energet B of t, it will be same B of t into AC cos omega ct, which is plus or minus AC cos omega ct. Because B of t we consider it as plus or minus 1. Bipolar energet is nothing but a signal having two polarities, high level as positive magnitude and low level as negative magnitude. Okay. So please remember this expression. Let us go to the next slide so that you can see the generation for BPSK. Already I said you what is the general expression for BPSK signal? B of t into AC cos omega ct. B of t into AC cos omega ct. If we want to generate the product of B of t and AC cos omega ct, which is nothing but the BPSK signal, what you can do? You should make use of bipolar energet. Okay, so that's why initially you need a level encoder or level shifter to convert unipolar energet into bipolar energet. Please observe the block diagram. First, our intention is to generate the bipolar energet. So unipolar energet is applied to the like a level shifter technique. Is applied to the level shifter to generate bipolar energet. We are representing bipolar energet as B of t. We are representing bipolar energet as B of t. Okay. So first we have generated the input signal. What is the input signal? Bipolar energet. Instead of unipolar energet, as we took in the case of BASK, here first we will generate bipolar energet and that is applied to the multiplier. So could you please recollect the generation technique of BASK, amplitude shift keying? In amplitude shift keying, the unipolar energet and carrier signal are applied to the multiplier. So multiplier output will be the product of unipolar energet and AC cos omega ct. And the unipolar energet, its magnitude is like 1 when the data is 1 and magnitude is 0 level when data is 0. So that's why in PSK we got AC cos omega ct for data 1 and for data 0 unipolar has 0 level. So it is ASK signal magnitude is also 0. But here in the case of bipolar energet, for the data bit 1 it has high level, that is positive level, and in the case of x of t 0, you will have, instead of 0 in case of unipolar, we will have -1 for x of t 0, +1 for x of t 1 and -1 for x of t 0. So that's why B of t is a bipolar energet which is equals to plus or minus 1. Its magnitude is +1 when x of t is 1 and B of t is equal to -1 for x of t 0. So now that bipolar energy is applied to the multiplier, and where other input is carrier component. If these two components are multiplied, you can generate BPSK signal as B of t into AC cos omega Ct. Here actually B of t into AC cos omega Ct. Okay, please write it as AC, B of t into AC cos omega Ct. I did not mention there. So next time whenever I upload the PPT, I will change it. B of t into AC cos omega Ct is the BPSK signal, where B of t is equal to plus or minus 1. So that's why upon replacing B of t as plus or minus 1, you can get it as plus or minus AC cos omega Ct, plus or minus AC cos omega Ct. Okay. So how can you generate BPSK signal? So almost all the principle behind generation of BPSK is similar to that of BASK. Okay. So in BASK, unipolar energy and carrier are applied to the multiplier. Okay. But in the case of BPSK, bipolar energy and carrier are applied to the multiplier. So what is the general form of BPSK signal? B of t into AC cos omega Ct, where B of t is plus 1 when x of t is 1, minus 1 when x of t is 0. So please observe the circuit as well as the statements shown above and below to the circuit. So unipolar energy is applied to the bipolar energy level encoder to generate bipolar energy B of t. Okay, next B of t and carrier are applied to the multiplier. So this product modulator multiplies B of t and AC cos omega Ct, so that the output is B of t into cos omega Ct. So you can get it as plus or minus AC cos omega Ct. So I can directly say that BPSK signal is equal to plus AC cos omega Ct plus AC cos omega Ct when x of t is equal to 1, minus AC cos omega Ct when x of t is equal to 0. Please remember this equation, B of t into AC cos omega Ct. B of t is plus or minus 1. Okay, let us move to the next slide. So let us go through the analysis part, what we did in the case of BASK. So in BASK we discussed by assuming the power dissipated per symbol as P suffix S. Okay, and let us take that as we know that it is V square RMS divided by R. So RMS value is maximum value by root 2 whole square divided by R, where maximum value is AC. Amplitude of carrier maximum amplitude is AC by root 2 whole square divided by R. So you can represent it as AC square by 2R. It is the same thing what we did in ASK and in earlier classes, first chapter also we did the same. Okay, so power dissipated per symbol we assumed it as P suffix S. So that's why you can get it as AC square by 2R. Now for normalized input, you can consider R as 1 ohm. For normalized input, you can consider R as 1 ohm. So power dissipated per symbol, you can obtain it as AC square by 2. Now how can we replace AC? Amplitude of carrier. The same thing we did in BASK. We replaced the amplitude of carrier as root 2 PS. Okay, root 2 PS, where P suffix S is the power dissipated per symbol. Okay, so what is the general expression for BPSK? B of t into AC into cos omega Ct. Okay, now how can we represent the amplitude of carrier in terms of power dissipated per symbol? Why we are representing in terms of power dissipated per symbol? In order to calculate the Euclidean distance. By representing the signal space diagram, we need to calculate the Euclidean distance. So in order to represent in terms of symbol energy, first we should represent in terms of power dissipated per symbol. Okay, so that's why we are replacing amplitude of carrier AC as root 2 PS. Okay, so B of t into root 2 PS into cos omega Ct. So it will be plus or minus root of 2 into PS into cos omega Ct. Now what is B of t? I think everyone know that B of t is plus 1 when input x of t is 1 and b of t is minus 1 when x of t is 0. Okay, so we can rewrite it, the generalized equation, as plus or minus root 2ps cos omega ct. Okay, now what is the general expression for BPSK? It is plus AC cos omega ct for data 1 minus AC cos omega ct for data 0. Replace AC as 2ps, root 2ps. So plus root 2ps cos omega ct when x of t is 1 minus root 2ps cos omega ct when x of t is 0. Okay. Now what is the thing we need to represent the power dissipated per symbol in terms of symbol energy? What is symbol energy? ES. Already we defined in ASK as symbol energy ES is equal to product of power and time. So power dissipated per symbol is PS into symbol duration is TS. Okay, thereby you can calculate the symbol energy. So notation for symbol energy is ES, capital E suffix S. It is equals to PS into TS, where PS is power dissipated per symbol. Now let us represent the above equation in terms of symbol energy. Let us move to the next slide. What we are doing here? B of t into, we are rearranging the equation. How we are rearranging the equation? We have root 2ps, but we need ps into ts. So to get like that, what we need to do? We have ps inside the root. So you need ts also inside the root. Okay, so that's why divide the numerator in denominator or multiply the numerator and denominator with respect to symbol duration. So upon rearranging the equation, our intention is to get in the form of ES, that is PS into TS form you should get. So B of t into root PS into TS into root 2 by TS, because here we have root 2PS. Take that root 2 outside and take root TS in the numerator inside the root of PS, so that you can get root PS into TS into root 2 by TS into cos omega ct. Now already you know that what is 1 bit energy carrier? Phi 1 of t. We know that if in case of the binary ASK or binary PSK or binary FSK, that is in case of binary transmission techniques, because we are transmitting only 1 bit per symbol, we will have only 1 bit energy carrier. If we transmit 2 bits per symbol, you will have 4 phase variations and 2 energy carriers. Because here 1 bit per symbol, here we will have only 1 bit energy carrier, that is phi 1 of t, which is equal to root 2 by ts into cos omega ct. Okay, so BPSK signal, how can we replace now? Here we have B of t as plus or minus 1. So B of t into root ps into ts into phi 1 of t, where ps into ts is equal to es. So you can write it as plus or minus root es into phi 1 of t, plus or minus root es into phi 1 of t. So it is equals to plus es into phi 1 of t when x of t is equal to 1. When x of t is equal to 0, it is equals to minus root es into phi 1 of t. Okay, so what is the general expression for BPSK signal? B of t into root ps into ts into phi 1 of t. Tell me in terms of symbol energy. B of t into root es into phi 1 of t. Okay, it is plus 1 when x of t 1 b of t, and it is minus 1 when x of t is 0. And in BPSK we know that bit duration equals to symbol duration, because 1 bit per symbol is transmitted. And what is symbol energy? PS into TS. Okay. Now let us move to the next slide to calculate the Euclidean distance. Okay. Okay. Prior to that, please let us see the BPSK waveforms. Generation of BPSK. Please observe here you will have 4 figures. First figure is First figure represents the binary energy. Binary data sequence, that is nothing but unipolar energy. That is nothing but the unipolar energy. Okay. And now we are going to convert that unipolar energy into bipolar energy. So a level shifter is used here. A level shifter is used to convert unipolar energy into bipolar energy. Please observe the figure here. First figure represents the unipolar. Why unipolar? For data bit 1, we have high level as a positive level. For data bit 0, it has 0 level. The magnitude is 0. Similarly, if you observe the bipolar energy, for the data bit 1, the magnitude is positive level. And for the data bit 0, it is negative level. It is not 0 level as in the case of unipolar energy. So it has signal flow is only in the positive direction. In case of bipolar energy, signal flow consists of both the polarities, positive and negative. Now third figure is the carrier wave. Third figure is the carrier wave. Fourth figure, how many inputs are there to the multiplier now? So for the multiplier, the inputs are bipolar energy and carrier signal. So in order to generate BPSK signal, what you need? You need a multiplier. You need a multiplier. And if you observe the output, so this is the output of multiplier. So what are the two inputs to the multiplier? Bipolar energy and carrier component. Bipolar energy and carrier both are applied to the multiplier. Okay. So for the data bit 1, because bipolar energy has positive magnitude, if you multiply these two, carrier with bipolar energy, you will get the same phase as that of carrier. But when data bit 0, for data bit 0, this bipolar energy has negative level. So if you multiply that negative magnitude with -1 with our carrier, what it will happen? So you will get shift in the carrier. How much shift? 180 degrees shift. 180 degrees shift between data bit 1 and data bit 0. So how can you like remember this? For data bit 0, you will have same phase as carrier. Sorry, for data bit 1, you will have same phase as carrier. For data bit 0, you will have phase shift of 180 degrees. Phase shift of 180 degrees. Because we have 4 zeros continuously, successively, said there is no phase change. But at the starting, you have 180 degrees phase shift. So after that, you have 2 ones. So no phase change. It is same as that of carrier. Okay, like that, for the data bit 1, the PSK signal has same phase as the carrier. For the data bit 0, PSK signal has 180 degrees phase change compared to carrier. Okay, but the amplitude and frequency remains constant. So what is the thing that you should remember here? The amplitude and frequency of PSK signal is same as that of carrier, except the phase change. How it will change? The phase is same as that of carrier for input x of t1. Phase change of 180 degrees for input 0. Okay, this is about the BPSK waveforms. Now one more thing I want to tell you is that if you observe the waveform, PSK waveform, it is almost all the waveform is similar to the DSBSC modulator, DSBSC signal. Because for a DSBSC signal, whenever you have like a magnitude in the input, whenever you have a magnitude change from 1 to 0 or from 0 to 1. Actually, we cannot say that the input is digital in the case of DSBSC modulation. There the input is message signal. So wherever you have 0 crossings, you will have, that is at the symbol bit duration, that is sample duration. In the case of AM, you will have phase reversal. phase reversal of 180 degrees. So the phase reversal of 180 degrees, the waveform resembles to that of DSPSC modulation. So here for generation of BPSK, we are using product modulator. Okay. What are the two types of product modulators? One is balanced modulator and other is ring modulator. Okay. So here we have used directly the multiplier. Okay. Let us move to the next slide. So please observe the signal space representation of BPSK. What is signal space representation? It is, please observe the phi 1 of t. So you are representing the signal in terms of 1 bit energy carrier. Here 1 bit energy carrier is phi 1 of t. Here the 1 bit energy carrier is phi 1 of t. Now, what is the magnitude of 1? What is the magnitude of phi 1 of t for input x of t 1? And so in order to represent signal space diagram, you should know the magnitudes of phi 1 of t when input x of t is 1 and input x of t is 0. We know the representation of BPSK signal in terms of phi 1 of t. What is the representation? Plus or minus root ES into phi 1 of t. Okay. So what is the expression for BPSK signal in terms of phi 1 of t? Already we calculated it as plus or minus root ES into phi 1 of t. Okay. So root ES is equal to root PS into TS. This is for data bit 1. And for data bit 0, what is the magnitude? Minus root ES. Minus root ES. So it is equals to minus root PS into TS. Minus root PS into TS. So what is the magnitude of 1 bit energy carrier? So what is the magnitude of 1 bit energy carrier for data bit 1? Root ES. What is the magnitude of 1 bit energy carrier for data bit 0? It is minus root ES. So let us calculate the Euclidean distance between the 2 points 0 and 1 upon the phi 1 of t axis. Upon phi 1 of t axis. So how can you calculate the Euclidean distance? It is the difference between the magnitude of 1 bit energy carrier for data bit 1 and data bit 0. Take the difference. For 1 it is root ES and for 0 it is minus root ES. So difference gives you the Euclidean distance. So root ES minus of minus root ES. So it is root PS into TS minus of minus root PS into TS. So it is 2 into PS into TS. Okay, where PS into TS, the product is nothing but the symbol energy. Okay, so please recollect the Euclidean distance for ASK. For ASK, the magnitude of for the data bit 1, the magnitude is root ES, and for the data bit 0, the magnitude is 0. So that's why the Euclidean distance for ASK signal is root PS into TS. Root PS into TS. But here how much? 2 root PS into TS. So it means that it is twice that of the, here the Euclidean distance is of PSK is twice to that of BASK signal, ASK signal. Okay. So as and when we know that as and when the Euclidean distance increases, the isolation between the 2 points increases. So it is very easy to recognize the bits at the bit levels at the receiver section. So its probability of error will reduce. So because the Euclidean distance of PSK is twice to that of ASK, the probability of error is almost all half to that of, is reduced to half to that of ASK system. So that's why this is the main advantage of PSK. Its probability of error is almost all, it's reduced because its Euclidean distance is increased to twice value that of ASK. So its probability of error is less. This is main advantage of PSK. And second advantage is, we know that BPSK is less susceptible to noise, but our ASK is highly susceptible to noise. Okay, because in ASK we have amplitude variations for the modulated signal. But here in the case of PSK, we don't have any amplitude variations. So that's why it is less susceptible to noise. And it has high immunity, high noise immunity. Okay, these are the two advantages of PSK over ASK. Let us move to the next slide. So already we calculated the bandwidth of ASK signal, and here also, because the principle behind the PSK generation and ASK generation is same, what we are doing in time domain, we are multiplying. So in frequency domain, you will get impulses at plus or minus Fc with a shift of plus or minus Fb. So that upper cutoff will be Fc plus Fb and lower cutoff will be Fc minus Fb. So here what is the bandwidth of BPSK signal? It is same as that of BASK, because the principle is same and principle for the generation is same. Okay, and it is shifted with plus or minus Fb from center frequencies. So that upper cutoff will be Fc plus Fb and lower cutoff will be Fc minus Fb. Okay, so that the bandwidth of BPSK signal will be 2 Fb. So what is the bandwidth of BPSK signal? It is equals to 2 Fb. Okay, so with this we can stop the session, and we have we can discuss the demodulation section in the next class. Okay. So any doubts in the today's session? Any doubts in the today's session? So please, any one of you kindly respond and tell me what is the general expression for BPSK signal. Please compare it to ASK. What is the general expression for BPSK signal? Any one of you kindly respond. So any one of the student, please respond. C2? C2. Tell me the expression for
Ma'am.
C2.
Yes, ma'am.
Tell me the expression for BPSK signal.
B of t into AC cos omega ct.
Please compare it to BASK. Please compare the same with BASK. Okay.